Hello friends, welcome to EC Academy.
In this lecture, let us understand morphological image processing. In image processing, mathematical morphology is used as a tool for extracting the image components that are useful in representation and description of regions such as boundaries, skeletons, and convex hull. So we can say the image morphology is used for extracting image components that are useful for representation and descriptions of the regions of an image such as boundaries, skeletons, and convex hull. So here boundaries, skeletons, and convex hulls are the different regions and shapes of the digital image. The morphological techniques are used for pre-processing or post-processing. So we can use morphological technique for pre-processing of an image or post-processing of an image. So we can use this for morphological filtering, thinning, and pruning. So here pruning is nothing but trimming of an image. The language of mathematical morphology is set theory. Set theory is the mathematical morphology representation of an object in a digital image. Now let us understand some basic concepts. Let us consider A to be a set in Z square where Z is two-dimensional integer space. If we consider A which is equal to A1, A2 which is an element of A, then we can write A belongs to capital A. If we consider Z as two-dimensional integer space, in that integer space, if we consider A that is at the coordinate A1, A2, then we can say A belongs to capital A. If A is not an element of A, then we can write A does not belong to A. The set with no elements are known as null or empty set that can be represented with phi. So the set with no element can be known as null set or empty set that can be represented with phi. A set can be represented by a content of two braces as shown here. The elements of the sets are known as coordinates of pixels that represents the object, and also it represents other features of interest in an image. So the elements of set are known as coordinates of the pixel that represent the object and other features of the image. Other features like intensity of an image. If every element of a set A is also an element of another set B, then A is a subset of B. So this can be represented as A is subset of B. So this is the representation of subset. If the element of A is also an element of B, we can represent it as A is subset of B. The union of two sets A and B can be represented as C is equal to A union B. The intersection of set A and B can be represented as A intersection B. So this is how we can represent the intersection of set A and B. Two sets A and B are said to be disjoint or mutually exclusive if no common elements are present. So that can be represented as A intersection B is equal to phi. So here it represents null. So if no common elements are present in the set A and B, then we can represent it as A intersection B is equal to null set, which is phi. The complement of a set A can be represented as A to the power of C is equal to W, where W does not belong to A. The difference between two sets can be written as A minus B is equal to W, where W belongs to A and W does not belong to B. So if we consider two sets A and B, here the term W will belong to A and W will not belong to B. This figure shows the example for the above set theory which we have explained. So the result of the operation is indicated in each figure with a gray color. So if we consider two sets A and B, so A union B is represented in this figure and A intersection B is represented here. So as you can see, this gray color represents the region which shows A intersection B. A complement is represented in this figure and A minus B is represented in this figure. As you can see, elements in A are represented in gray, which means only this region represents A minus B. So we are subtracting A from B. So the region that is covering B is subtracted and the remaining region is considered here. The reflection of set B can be represented by B cap. So here B cap can be written as W, where W will be equal to minus B, where B belongs to capital B. So the reflection can be represented as B cap is equal to W, where W is equal to minus B. The translation of set A by point Z is equal to Z1, Z2 can be represented as AZ is equal to C, where C will be equal to A plus Z. Here small a belongs to capital A. So this is the representation of translation of an image, and this is the representation of reflection of the set B. So as you can see, this is the representation of set B, and if we take the reflection of this set, we'll get in this form. So it is just the reflection operation of set B. Now let us understand some logical operations. The logical operation provides the powerful complement of implementation of the image processing algorithm that are used on morphology. So logical operation provide the powerful complement for implementation of image processing algorithm that are used in morphology. The principal logic operations that are used in image processing are AND, OR and NOT operations. Here NOT operation is complement operation. So these are the principal logic operations that are used in image processing. And also we can combine any of these logical operations to obtain other logical operation. The logical operations are performed pixel by pixel basis, which means the logical operations are performed between corresponding pixels of two or more images, except for NOT operation. So NOT operation is performed on the pixel of a single image. This figure shows the various examples of logical operations involving image where black color or gray color indicates binary 1 and white represents binary 0. Here if we take an image A, if we perform NOT operation, we'll obtain the opposite of the image A, which means the white pixels are converted into black pixels or gray color and black pixels are converted into white pixels. That is nothing but your NOT operation. If we perform AND operation by considering two images, if these two images are considered for AND operation, so this is the resulting image where the common region is converted to black and other region is in white color. So if we consider similar two images, if we perform OR operation, the region that are common between A and B are black color and remaining part of the image is in white color. So this is the representation of XOR operation and this is the representation of NOT AND operation. So if we say NOT AND operation, which means we need to consider NOT A and B. So it is the combination of NOT AND operation. This is about some basic concepts of set theory and logical operations in morphological image processing. In the next lecture, we'll understand dilution and erosion in morphological image processing. Hope you have understood this topic. Thank you.